Good morning, everyone. My name is Alexey Tumanov. I'm going to be talking about federated learning for multi-capacity DNNs today. Is everything okay? He's giving me this look like something is not okay. Oh, you want this behind the ear. Okay, I see. Test. Yeah. Good morning. We're going to be talking about federated learning for multi-capacity DNNs, or as advertised, cost-efficient federated NAS for on-device inference. My name is Alexey. I come here from Georgia Tech. I work on the intersection of systems and machine learning. So first of all, what I would like to do is I would like to build the intuition for why we care about multi-capacity DNNs. As we all know, machine learning applications are increasingly deployed in dynamic and unpredictable conditions. And in such situations, what we have is that more and more we care about both latency and accuracy at the same time. Both of those constraints are critical. Furthermore, machine learning applications are increasingly running on resource-constrained devices that are forced to choose between accuracy and latency because you don't have abundant compute in all cases. And that, in addition to this, what's complicated is that it must be done rapidly in order to avoid missing deadlines. So let's take a look at this toy example. This example is sort of drawn from the cyber-physical systems, in this case an AV car. You have a car that's, for example, navigating through an urban terrain, a lot of things going on. You have to predict, or basically you have to perform object detection on the street, on the street signs. You have to perform classification for the objects moving on the road. And in order to avoid the collision, you have to make the decision really, really fast on the left-hand side. And so maybe to make sure that you actually satisfy this deadline, you could do that with a lower accuracy model. Whereas on the right-hand side, if you're driving through an urban terrain, the complexity of the queries is a lot less because the frames that you're drawing from the onboard cameras don't really have as much work to do, essentially. And so you have more time to make those decisions, let's say 20 milliseconds instead of 2 milliseconds. And so you can actually afford to spend more time on this compute at higher accuracy. So in one case, this example should motivate that in one case you might be willing to use something that is to the further left in the accuracy latency trade-off space, while in the other case you might be willing to use something that's to the top and the right hand part of this latency accuracy trade-off space. What I'm trying to emphasize here is that the important takeaway from this slide is that I don't think that the single point in this latency accuracy trade-off space is sufficient. While state-of-the-art focuses on optimizing for a single point in the latency accuracy trade-off space. So what we want to be able to do is we want to be able to train a family of models. We want to be able to train a set of latency accuracy options at the same time, cost efficiently. But the question is how? So I mentioned dynamic deployment scenarios at inference time. Let's very briefly talk about what are the sources of that dynamism. First of all, you have different hardware types. That one is a pretty straightforward and it's a pretty well-studied problem in the federated learning literature. But we also have variable traffic and latency constraints, and we also have dynamic resource availability, such as, let's say, this trace that was drawn from Microsoft Azure Functions. You can see that it's very spiky, and the spikiness is over a very large and wide range of throughput in queries per second, in this case from 5,000 to 9,000 queries per second. We also have to deal with the dynamism associated with how much power and energy you have left on the battery on the device where you're performing inference. Another motivation for federated learning has been pretty well studied, and of course, healthcare is a poster child for federated learning because of the privacy considerations. So why we want to do FL? One of the motivations for FL is to maintain the privacy of the patient data, right? So in this particular case, you have multiple hospitals. Those hospitals have edge clusters, and they have some private data they want to train over, and they cannot share that data. So basically, you have a secure cloud where you aggregate model updates, and you send the updated model to the individual hospitals to perform some local updates on the local cluster data, on the local patient data. And of course, another poster child for federated learning is the cross-device case where you have Gboard and the next word prediction task here that's operating in a very different regime across a much bigger number of clients with a lot more heterogeneity. And in this particular case, the model that's being trained is the next word prediction model. Okay, so here are some backgrounds and trends. Overall, what we are observing is that we have increasing and growing heterogeneity in the privacy-sensitive data and compute. So in terms of privacy-sensitive data heterogeneity, this has been emphasized in literature. For example, there's this Nature Medicine journal that published a paper on federated learning for predicting clinical outcomes for patients with COVID-19. The heterogeneity of data, extreme heterogeneity of data, is something they explicitly pointed out. And this is a cross-hospital study that was quite interesting from federated learning perspective. If you haven't had a chance, I encourage you to take a look. There's increasing heterogeneity in compute. You have to deal with all sorts of static and dynamic heterogeneity in terms of the bedside compute that you have, in terms of the edge cluster compute that you have. But there are also some newly emerging challenges that are quite interesting, that are much more dynamic. So the dynamic factors that I previously mentioned are query traffic, complexity, power levels, and latency deadlines. Okay? So here's a kind of an anchor slide. What is the goal of our work? The goal is to come up with privacy-preserving distributed training regime where we train once and deploy for multiple scenarios. And we take care of the static parameters, such as the deployment hardware, as well as dynamic parameters, the real-time parameters that change while your application is running. So that includes query complexity, power level, query traffic. The proposed solution, how the mechanism that we are trying to use for this is the weight-shared supernet training in federated setting. And the key takeaway is the following. What are we trying to do? We're trying to build, or we're trying to train Pareto frontiers with asymptotic complexity of order 1 in a federated fashion. Okay? Pareto frontiers per client in order 1 in a federated fashion. How are we trying to do this? The mechanism for this is weight-shared DNNs. Why do we care? Why federated? Privacy preservation. Why weight sharing? Is because it gives us the ability to produce this family of models instead of a single point that a lot of the state-of-the-art continues to focus on to this day. So just to reemphasize, we have federated learning state-of-the-art, where you have a server in the middle, this blue cloud right here. It actually basically sends the updated model to the clients. The clients are performing some local updates. They aggregate it back on the server with all sorts of bells and whistles. But fundamentally, at the end of the training, what you end up is a single point per client in the latency accuracy trade-off space. That's state-of-the-art. What we want to be able to achieve, as I mentioned, is a family of models per client. How do we do that? Well, the conventional approach would be to basically train a different neural network for every single different deployment scenario that you care about. And this is what you see at the very top. Clearly, this is very expensive, right? More recently, in a centralized setting, there was a paper in iClear 2020 that basically proposed weight-shared approach in a centralized setting that actually does give you a cloud of points in accuracy latency trade-off space. And the claim to fame for this paper is the separation of training from neural architecture search. They've performed training for this super network in a centralized setting, and then they extract they have the ability to extract subnetworks post-training without fine-tuning. We improved on that work in iClear 2021, where we basically improved the cost efficiency of this by focusing on training the points that we believe using some heuristic, is closer to the Pareto frontier of optimality. Okay, so as I mentioned, state-of-the-art is centralized weight-shared DNNs. Weight-shared DNNs are obtained by adding elasticity to the DNN dimensions. The supernet is formed, it forms a comprehensive and a large model, and then subnetworks they differ in several elastic dimensions. They partially share their weights, and they can be directly used for predictions without any further retraining. So that last part is very important. And the weight-shared DNNs include a rich trade-off space between accuracy and latency, which is what we wanted initially based on our initial set of motivation slides, right? So just a few words of how we, in terms of how we achieve this elasticity. Let's take a look at this residual network. It's typically constructed by stringing together a bunch of stages. Each stage consists of some number of bottleneck blocks. And basically, the way we achieve elasticity is by looking at the depth, width, the kernel, and resolution, and making them elastic. So just as an example, let's take a look at this. We have some n stages, and we have each stage consisting of 4 bottleneck blocks. So in this particular case, this is the maximum number of bottleneck blocks that you have per stage. And we have this D list that keeps track of how many bottleneck blocks we keep per stage. So the ith element of D corresponds to how many bottleneck blocks we have per stage. But we could also skip some of the blocks. So in this particular case, instead of the maximum number of 4 bottleneck blocks per stage, we have two bottleneck blocks per stage. We can also have everything in between independently across stages. And we have another parameter that keeps track of the multiplication factor that basically controls the width of the bottleneck blocks that are used for each of the stages. Okay, so this is just an illustration of how you would achieve different dimensionality in the subnetworks. At the end, what you get is a point cloud. On the x-axis here, you have flops. On the y-axis, you have test accuracy. And of course, what we care about is the Pareto frontier of this point cloud. In other words, for any given flop budget, we want the highest accuracy model, or for any threshold for accuracy, we want the lowest flop budget achieving that accuracy. Okay, so the top left is the best, and this is what we want to achieve per client. Right, so this brings us to the proposal. Superfed achieves this with weight-shared federated training. What we have is a server that keeps track of the super network, and the super network sends the subnetworks to the clients for some local update. And the critical difference here is on the right-hand side of the slide, where instead of producing a single point per client, at the end of training, what you achieve is a Pareto frontier. And that's the key qualitative difference. Of course, the first challenge to achieving this is subnetwork distribution. We have to think about 2 things. First is the spatial component. I call it spatio-temporal subnetwork distribution. The spatial component basically says which specific subnetworks are sampled from a supernet and which clients they go to for that specific round R. So that's the spatial part. The temporal part is that there's also temporal dynamics, the load balancing across time. Basically, what this keeps track of is over time, where do we send the minimum subnetwork, where do we send the maximum subnetwork, and in general, how do we load balance these subnetworks that was sampled from the supernet across clients over time. And so for the spatial, the way we sample this is what's called sandwich sampling. And what it does is it samples the smallest and the largest subnetwork per round, at the very least, and some number of subnetworks randomly sampled in between. And the temporal component is basically done by tracking the largest and the smallest networks that are seen by every client. So what we do is we assign the smallest network to the client which has seen it the smallest number of times. And so we have an illustration for this. Horizontally, you have time. Vertically, you have your clients. So vertical is the spatial dimension. Horizontal is the temporal dimension. You have client IDs 0, 1, 2. And we are keeping track of the maximum and the minimum network count that each client has seen. So during round 0, we send the minimum subnetwork to client 0 and the maximum subnetwork to client 2. So we increment the black and the red count. For round 1, basically what we did is we sent the maximum subnetwork to client 0 and the minimum subnetwork to client 1, and so on and so forth. So for every single round, we make sure that we send the minimum and the maximum subnetworks to the clients that have seen it the least. And this is the temporal load balancing component. Very simple, but very effective technique. The second challenge is, what do you do at aggregation time? Because now, instead of sending the same architecture to every single client, right, which is pretty homogeneous, and you just perform some sort of federated averaging at the end, you have variable subnetworks to deal with that are weight shared. You know, they're not independent, they're weight shared. And here's an illustration of this. So let's say that you sample the minimum subnetwork on the left-hand side and the maximum subnetwork on the right-hand side. So here, what this shows is a single stage that on the left-hand side consists of 2 bottleneck blocks with an expansion ratio of 0.1. On the right-hand side, it consists of 4 bottleneck blocks. So the dot, dot, dot here corresponds to the 2 missing bottleneck blocks. And the expansion ratio is 0.25. And each of these rectangles is weight shared across the 2 clients, okay? And so there are 2 different approaches to dealing with aggregation. The normal one is just sum it up and divide by the cardinal overlaps. Okay, so if for a particular weight it was contributed to by, let's say, 3 clients, then you sum it up and divide it by 3. If it's by 2 clients, you sum it up and divide it by 4, sum it up and divide it by 4, and so on and so forth. That's pretty straightforward. What we are doing is we are using the weighted average approach, where we favor the weights that are coming from a specific subnetwork more, and there are reasons for that. Okay, and so we aggregate overlapping weights with more weight assigned to the maximum network contribution. We account for variable cardinality of overlap, and on top of this, we decay basically this priority given to the maximum network, the max net weight, over time, using the parameter beta that's assigned to the largest network contribution. So what we do is we assign 1 minus beta over C minus 1 assigned to all the remaining C minus 1 client contributions. And the beta is decayed from 0.9 to uniform. Of course, this is a hyperparameter as the rounds proceed. And we can do the decay itself in various different ways. We've tried linear decay and cosine decay. Cosine decay performed the best. And so to summarize, the spatiotemporal weight shared FL training, it sort of consists of these 3 components. The first one is the subnetwork distribution, which includes tracking sandwich sampling, and it includes the temporal load balancing. And the second part of this is what do you do at aggregation time, which includes the decaying maximum network favored weight shared average. So, how are we doing in terms of evaluation? First, we tried this technique over a number of different data sets, CIFAR 10, CIFAR 100, and CINIC 10. And the setup here is that we used the Dirichlet alpha parameter of 100, which basically corresponds to pretty homogeneous data with client participation ratio of 0.4. And the number of clients for these 3 workloads was 20 for CIFAR 10, 20 for CIFAR 100, and 100 clients for CINIC 10. And basically the comparison here was with federated averaging, where each of the points that you see, each of the blue diamonds, was independently trained. So remember, the goal is for us to achieve a Pareto frontier per client, right? One of the mechanisms using state-of-the-art techniques is to train these different points on a Pareto frontier independently using state-of-the-art techniques. And the comparison is across the Pareto frontiers that you achieve, either using our proposed technique, which is in this case superfed, or using the state-of-the-art techniques. So higher is better, the orange is us, and we are outperforming independently trained federated averaging in all cases, and the performance is robust across different data sets and the different number of clients. Okay. Now, what happens if we change and vary the client participation ratio? With the client participation ratio of 0.2, 0.4, and 0.8. In this particular case, we set the number of clients to 20, and the statistical heterogeneity was mostly homogeneous. Some observations are that you can see across the slide is that we have an increasing gap between I-federated averaging and superfed with the increasing participation ratio. I-fed average accuracy suffers from the greater client participation. We believe that the reason for this is the interference when you don't account for basically the aggregation of contributions from multiple subnetworks. Okay, so in terms of cost of training, because remember what we are doing is we're trying to do it in a cost-efficient way, we're looking at computational cost and communication cost. So on the left-hand side, we have computation cost, and as you can see, one of the goals from the very beginning was to make sure that the cost we're paying is asymptotically order 1. And this is what's seen here. No matter what the model family size that you have, right, the cost that we're paying for producing this model family size is constant. And that's a very good property to have, because regardless of the density of the Pareto frontier that you want to be able to achieve, you're going to pay a fixed cost for that. Using state-of-the-art techniques that don't have this asymptotic property, of course, you are going to have some sort of monotonically increasing cost function as a function of model family size. And this is exactly what you're observing here. And we stopped it at the model family size of 9, but obviously it's going to keep going, and the gap is going to keep spreading. And so from the perspective of publication, I could report 1 order of magnitude improvement in cost performance, 2 orders of magnitude improvement in cost performance, whatever you want, depending on the model family size. Here, we just stopped at the model family size of 9, and we demonstrated that even for as few as 9 points on the Pareto frontier per client, we're able to reduce the computational and communication cost by an order of magnitude. Okay. We also looked at the effect of data heterogeneity, because remember I mentioned that this is a big problem. So here, we're taking the following approach to data heterogeneity. So on the left-hand side, we're using the Dirichlet distribution in order to simulate data heterogeneity across classes and clients. So horizontally, you have the client IDs from 0 to 20. Vertically, you have the class numbers from 0 to 9, so 10 classes in total. And basically, the diameter of this dot corresponds to how much this particular class for this particular is represented on this particular client, right? And so as you increase this alpha parameter for the Dirichlet distribution, you're going to see an increasing heterogeneity in the diameters of your colored dots. And this corresponds to increased statistical heterogeneity, which creates a problem for most federated learning algorithms. Okay. So how are we doing with respect to statistical heterogeneity? So on the left-hand side, mostly homogeneous, alpha equals 100. In the middle, we have some heterogeneity with alpha equals to 1. On the right-hand side, we have alpha equals to 0.1, mostly heterogeneous. You can see that higher is better, orange is us, and we are outperforming the independently trained federated averaging. And in addition to this, we're also robust, or more robust, to the increase in statistical heterogeneity compared to federated averaging. So, in summary, where I started with is by saying that applications across many domains, including augmented reality, virtual reality, healthcare, machine learning for healthcare in intensive care units, they're increasingly dependent on machine learning, and they increasingly care about both latency and accuracy at the same time. And so for that reason, it stands to reason that no single model is sufficient to serve applications like this, even when you're running a single application running on a single device. So one application, one device, I argue that you want a Pareto frontier even in that particular case, okay? Because of all of that dynamic heterogeneity that's happening. So what that means, sort of by implication, is that we need to be able to train a family of models, and we need to be able to do that cost efficiently, of course, while preserving the privacy of the data. So what we have proposed is we've proposed one mechanism to achieve this, and that's called weight-shared federated learning. And our contributions to that are twofold. The spatio-temporal subnetwork distribution. What that means is that you make a decision which subnetworks to subsample and which clients to send them to for a given round R. And you load balance that over time. And the second component of the contribution is what do you do at aggregation time? Basically, how do you perform model parameter aggregation with arbitrarily variable overlap? The takeaway results is, as I mentioned, I can put any order of magnitude here depending on the density of the Pareto frontier that your application cares about. Let's just pick one, order of magnitude savings in compute and communication cost. We are matching or exceeding state-of-the-art accuracy, and we are robust and generalizable across data sets, client participation ratios, and heterogeneity levels. On that note, I would like to conclude. Thank you everyone for your attention and open it up to questions. And I would like to keep the slides on.
Hi, thank you so much for the presentation. Just a quick question. So I want to ask about the convergence in terms of the global rounds required. So your method versus the independent Fed average. So how many rounds are required? What is the impact? Because we are sampling and then sending it to independent clients. So what does that affect? How does that affect the global rounds required?
Both were. So first of all, we didn't do theoretical analysis, so I don't have anything to say in terms of the theoretical guarantees of convergence. From the experimental setup perspective, we used the same number of clients, same number of rounds for both.
Thank you.
Yeah. Yeah, because otherwise this would have been reflected in the cost calculation. Yeah, so we wanted to make sure that the cost calculation is fair and apples-to-apples comparison.
Hi, Alex. Great talk. Thanks. One question is on the sandwich part that you mentioned. And during partial, so you assume partial participation with different participation rates. During federation, do you assume that you always have a client that can run the maximum model of your supernet?
Yeah, that's a very good question. So. From the perspective of this presentation, yes, that is the assumption that is being made by the algorithm. However, we can relax that assumption because all we care about is 100% coverage for model parameters. So basically, for any given round, the invariant that we want to be able to sustain is that every single model parameter has been sent to at least one client. One way to do that, in a very simple case, is just sample maximum network, because then you're guaranteed 100% coverage of model parameters. But you don't necessarily have to do that, but then that complicates the sampling procedure, right?
Yeah. Thank you.
Yeah. That's a great question.
Right. Hey, Alexey. So,
hey.
Nice talk.
Thank you.
One question I'd like to ask is, in your premise, right, you talk about latency, sensitivity in various domains, and I think we agree that's usually thought of as an inference time question. Mm-hmm. And here you're talking about basically the how to train this family of models. That's right. And so have you considered what happens when these devices that are training models, right? Do you envision that they are performing training at the same time they're using resources to perform inference? And if what's the case, then how does the fact that these federated devices are performing training, how does that compete? How can that be balanced against the set of resources that they need to use for inference? Does that require them to store the full family of models on each device, or they're going to be stuck with whichever, sandwich layer of the model that you've given it, right? So these are the questions that pop in my mind, the relationship between training and inference, and what happens when they're occurring on the same device as I seem to be reading from your setting. Mm-hmm, mm-hmm.
think I'm still on the mic. Okay, good. Yeah, that's actually a very good question. In some sense, sort of the resource management aspect of this, when you're running both at the same time, is orthogonal to this work. But given that we are focused on both inference and training here, it's definitely something that we're thinking about in a separate project. It's a great question. It's subject to open debate and open research. You could imagine different kinds of approaches to this, like, for example, performing statical partitioning of the resources that you allocate for training and inference, especially in the case where inference is trying to maximize latency SLO attainment. You want to make sure that you're operating within some predictable resource envelope. And then sort of the rest of the resources that you have available, you can allocate for the purposes of training. This is slightly sort of less fulfilling for us from the SysML domain. Especially given the fact that over time you're sending different sized models to different clients, you can definitely take advantage of that. And so whenever you receive a certain sized model, you can reallocate the remaining capacity of the device for the purposes of inference. So that's actually, I really like that question, because you can transiently and intermittently increase the serving capacity of the device depending on what size subnetwork they actually have to train at any given round.
Right, and you saw where I was, you got where I was going with that question, right? Because then the question becomes, does that open new opportunities in the policy by which you send subnetworks, right? Right now, it's essentially kind of like fairness-based, right? You want to make sure everyone's seen the maximum and minimum subnetworks a certain amount of times, right?
Yeah.
And then, as we all know in scheduling, right? Fairness is the antithesis of
performance.
Of fulfillment, exactly.
Yes.
So once you start enforcing fairness, what happens to the devices that I got a latency problem, I need to get this now on my self-driving car crashes, as in your diagram, right? Then you start getting all the really interesting questions in scheduling, right? So I thought it was pretty cool to think about that.
Yeah, and it actually goes both ways. For example, if for this particular worker, I have a queue that's building up with queries, so I know I need to transiently increase the serving capacity of that particular worker, I'm going to communicate a reduced capacity for the subnetwork size that I'm able to receive at this federated round R. And so, that can be propagated to the server, and the server will honor that transient capacity constraint.
Right.
And so what you're essentially doing is you are sampling the subnetworks on the client side within the time variable envelope of the client capacity, of the client model size capacity. And what's interesting is that our mechanism of subnetwork sampling actually allows for that. So notice that if we are constantly sending the same kind of model architecture to all the clients, it doesn't have that flexibility. And so we left it outside of scope for this particular work, the dynamic training time heterogeneity on the client perspective, but this plays really nicely with training and inference overlap workload.
Right, it makes sense, right, with the fact that you're stochastic about how you send things to, devices means that you can tolerate up to a certain amount of unfairness without becoming grossly unfair in a way that disincentivizes the participating devices.
Yeah.
Cool. All right, thanks for answering the question.
Yeah, thank you. Great question. Anybody else?
Let's thank Alexey.
Yeah. Thank you.